Hey folks, here's a short screencast on indeterminate forms. I'm just going to do an example. I'll probably do a couple others in separate screencasts. This one's going to be a little bit silly, and you'll see why. So let's look at the limit as x goes to infinity of e to the x to the x. So notice as x goes to infinity, e to the x, it's also going to infinity, and 1 over x up here is going to 0. So this is an indeterminate form of the type infinity to the 0. The base is getting big, the exponent is getting small. Which of these forces is going to win? Is it going close? Is it going to get close to 1? Is it going to get bigger and bigger? Who knows? It's indeterminate. I'll return to the explaining why this is sort of a silly example, but let's just keep going forward with this. We want to use L'Hopital's rule. L'Hopital's rule does not apply to indeterminate forms like this directly. We have to do some algebraic manipulation. So let's write y equals e to the x to the 1 over x. And because there's a variable in the exponent, we take a logarithm of both sides. And then we can use properties of logarithms to get that exponent down. I'm just going to keep writing it like this. I could do some more algebraic simplification, but let's just stop here. And now notice, if I write this like this, the numerator goes to infinity, and the denominator now goes to infinity as x goes to infinity. So this would be an indeterminate form of type infinity over infinity. That is, I'll write that again, the limit as x goes to infinity of the natural log of y, right? This right here, which is the same as this, is an indeterminate form of type infinity over infinity. The numerator is a perfectly well differentiable function, the denominator too, so we can apply L'Hopital's rule. So L'Hopital's rule says the limit of our logarithm is the same as the limit of the ratio of the derivatives. So the derivative of x is 1. The derivative of log e to the x, that's 1 over e to the x times e to the x. And those e to the x's cancel. That's pretty sweet. So you get 1 over 1, so that limit is just 1. So it's continuing up here. Since the limit as x goes to infinity of log y, is 1, what we want is the limit as x goes to infinity of y, so we're going to write this. The limit as x goes to infinity of y is the same as the limit as x goes to infinity of e to the log y, using an identity for inverse functions, in this case the natural log and the natural exponential. And now a property of continuity is because e to the x, or because exponentiation is a continuous function, I can move this limit from the outside to the inside like this. And now this is the limit we just canceled, right? Or calculated, right? Its limit was 1. So this is e to the 1. So we conclude the limit as x goes to infinity of e to the x to the 1 over x is 1. Oh, not 1. Silly. Is e. Right, and that's the final answer. Right, so let me return to why I said this here was a silly example. Now let's go to the next page. The limit as x goes to infinity of e to the x to the 1 over x. Well, notice you can use the law of exponents. This is the same thing as the limit as x goes to infinity of e to the x times 1 over x. but that exponent is just 1. So our limit is just e. So you can see we got the same answer, different route. Didn't have to use any calculus. It just used algebra. So it verified our L'Hopital rule calculation here. But this is a good way to illustrate how to use L'Hopital rules for indeterminate forms that have an exponent in them. All right, that's it. See you in class.